Modern digital forensics deals with targets beyond the physical server rack. High-value evidence is now distributed across layered, virtualized environments existing entirely as software. When an investigator responds to an active attack, the most critical data, the actual footprint of the attacker, often exists exclusively in running processes and volatile memory. This creates a direct conflict with the traditional standard operating procedure for digital forensics. Historically, investigators have relied on Deadbox forensics, where the immediate reaction is to pull the plug on the machine to freeze the system and preserve the static storage platters. Applying that exact same Deadbox procedure to a virtualized environment or an active network intrusion destroys the investigation. Powering down an active virtual machine irreversibly erases the attacker's volatile footprint. The running malware, active network connections, and the unencrypted passwords are wiped clean the second the power is cut. System administrators often assume that a saved virtual machine snapshot provides a safety net, but a snapshot only records specific state changes at the exact moment it was taken. It does not capture the full active picture of a live intrusion. To capture this evidence without destroying it, investigators must abandon the Deadbox approach. They have to map the layers of software running these virtual systems and execute a tactical, real-time live acquisition. The first step of a live extraction is locating the virtualization layer. This is the software that actually runs and manages the virtual machines, known as the hypervisor. In an enterprise-scale network, you will typically encounter a Type 1 hypervisor, such as VMware vSphere or Microsoft Hyper-V. These are designed to run directly on the physical hardware, or bare metal, and do not require a separate operating system to function. This visual illustrates the difference between that bare metal approach and a Type 2 hypervisor. Instead of loading directly onto the hardware, a Type 2 hypervisor rests on top of an existing host operating system, like Windows or Linux. When investigating an individual suspect's device, Type 2 hypervisors are the ones most frequently found running localized, hidden virtual environments. Uncovering them requires checking specific forensic indicators. On a host machine running Windows, you look in the Users or Documents folders. In Linux environments, you check the user directories for any VM installations. You also need to examine the host's registry and system logs. These records will reveal if a virtual machine was recently run directly from an attached USB drive. One of the clearest ways to confirm the presence of a hidden virtual machine is to check the system's network adapters. In this control panel window, alongside standard Wi-Fi and Bluetooth connections, we see specific adapters for a VirtualBox host-only network and a VMware network. Once the virtualization software is located, you identify the specific file extensions that dictate the virtual machine's existence. It starts with pre-configuration files, usually labeled .ova or .ovf. Next are the virtual hard drive files, which store the actual data. VMware uses .vmdk, while VirtualBox uses .vdi. But the highly volatile immediate artifacts reside in the .vmem files, which serve as the virtual machine's RAM. Because virtualization tools use proprietary formats, forensic software often requires you to convert files, like a .vdi, into raw or universally readable image formats before analysis can begin. Identifying these files maps out the architecture of the suspect's machine. But successfully extracting the live data from within them requires a strict, time-sensitive protocol known as the order of volatility. Imagine an active network intrusion is underway. The investigator has a narrow window to extract data without altering the system state or alerting the suspect's guest operating system. To navigate this, they rely on the order of volatility. As this timeline shows, this dictates exactly how long information lasts on a network. Data in RAM and running processes might survive for only milliseconds, while data stored on hard drives can persist for years. Because of its rapid decay, physical memory, the RAM, is the absolute highest priority during a live acquisition. Capturing the RAM secures the artifacts attackers leave behind in real time: unencrypted passwords, login names, partially written instructions, and hidden open network sockets. Once the RAM is secured, the investigator moves down the sequence. They capture the system logs next, followed by active network traffic, and finally, the physical or virtual drive. Throughout this entire sequence, investigators must minimize their forensic footprint. The golden rule of live acquisition is that you never write collected data back to the target disk. All physical memory copies and collected RAM data must be routed immediately away from the target, directly to a secure network drive or external storage. When it comes to extracting this volatile data, investigators must choose between graphical user interface forensic tools and command line interface tools. Command line tools are more effective for this task. Graphical user interfaces require heavy system resources, which alters the state of the machine being investigated, and they frequently trigger false readings within Windows environments. For Linux-based live acquisitions, the process requires specialized command line tools like Volatility or Lime to cleanly handle the many different kernel flavors involved. Adhering strictly to the order of volatility secures the raw memory. But to locate evasive malware hiding inside a live system, investigators must deploy remote agents to parse the file system while the target is still actively running. Often, the target virtual machine is located across a corporate network or miles away. In these cases, investigators rely on remote acquisition tools, such as Belkasoft R or Magnet AXIOM Cyber. These tools allow examiners to acquire disk and memory data from remote Windows endpoints, and even access complex cloud instances like AWS S3 buckets. The extraction works by deploying an application known as an agent to the target endpoint. This establishes an encrypted secure sockets layer, or SSL tunnel, to safely exfiltrate the data without alerting the user. This remote live connection is necessary to bypass a common evasion tactic. Advanced malware programs frequently change their names and delete themselves to hide their presence from standard directory searches. Investigators counteract this by using the Windows DOS command fsutil to extract deep log data directly from the hidden USN Journal file, giving them a raw feed of file system activity. Executing the fsutil USN read journal C command on a live system requires administrative privileges, but it yields a precise timeline of exactly how a file is behaving. Looking at the raw output generated by the fsutil command here, we can see the exact moment a file is generated. The log clearly lists the file name as quotes.txt, and the recorded reason is file create. By tracing the timeline forward in the journal, we see the suspect file begin to change and grow. Moving to this next block of data, the reason updates to data extend alongside file create, showing active modification. Finally, the log exposes the malware's evasion tactic. The bottom two blocks record the exact moment the file alters its identity, contrasting rename old name for quotes.txt with rename new name as it changes itself to myquotes.txt. By executing this remote journal parse, the investigator successfully tracks the malware's entire lifecycle in real time. If they had simply shut down the system to scan the drive, this active behavioral evidence would have been lost. Back at the investigator's secure forensic workstation, the extracted components, the .vm RAM file, the .vmdk disk file, and the network logs, are now safely gathered. From here, there are two primary methods for analysis. The first involves mounting the extracted virtual machine as a static external drive, using tools like FTK Imager. This allows the VM to be examined using the same standard procedures applied to a physical hard drive. The second, dynamic analysis method, involves making a copy of the forensic image and booting it as a live virtual machine within a secure sandbox. This allows the investigator to safely observe the malware's behavior without risking their own network. If the investigator had followed traditional protocols and pulled the plug on the physical host, these active network connections, RAM caches, and real-time evasion logs would have evaporated. Modern digital forensics requires mapping virtual topography and executing live protocols to capture the exact state of the machine at the moment the crime occurred.